So thank you for the introduction, and thank you for having me today to this week of Manutech-SLEIGHT. So I'm gonna talk about the detection of contextual anomalies in attributed graphs. So this is my work with Christine Largeron and Baptiste Jeudi. So to give you a quick example, here we have a company A and a company B, which have a CTO, an employee, a CEO, and a fraudulent accountant. So we have an expert that tagged the company A as an anomaly, and we wonder whether company B should be also an anomaly or not. So to answer this question, we will train a model that can detect contextual anomalies by assuming that they are induced by a local context, such as being a rich company and having a fraudulent accountant. So in our case, we will use colors, and contextual anomalies are nodes of the graph whose local context exhibit a singular arrangement. That is, for example, on context 1, we have a node that has no color, and it has a green neighbor and a blue neighbor. So this will be our context B and G. On context 2, we have a yellow node. So this could define a context 2, so it would be denoted as Y bar. And on context 3, we have a blue node that has a green neighbor, and it would be denoted B bar and G. So these could all be context that defines anomaly. And more formally, we can have a graph G with a set of nodes V, a set of edges E, and some feature matrix X. And we will consider that there is an unknown small subgraph that we will call a context, and a distinguished node in this subgraph, such that each time this subgraph occurs in the data, then the corresponding node is the anomaly. And our goal is to find the anomaly, but we don't know the context. So there has been many people working on graph anomaly detection, and there are many kinds of anomaly, such as bridges between communities in graph, anomalous edges or irregular subgraph, and we have also near stars, near clicks, and dominant edges, for example. These are many kinds of anomalies that exist in a graph. A very interesting case is this kind of anomaly, which is on the left, we have a community, and on the right, we have another community. On the left, they are all orange, and they have features 0, 0. And on the right, they are all green, so that's the second community, and they have all features 1, 1, except one node on the red arrow that has features 0, 0. So this is a node whose features deviate a lot from those of their neighbors. And this could define a kind of anomaly. But in our case, in the case of contextual anomalies, to detect them, we're going to use graph neural networks in a semi-supervised setting. And to sum it up, we just want to learn a mapping function f that gives a new representation h'0 from previous representations h0 to h4. So on the graph here, we have a node 0 with some neighbors 1, 2, 3, 4, and a new representation will be learned based on the previous representation h0 to h4. So our biggest issue is that there is no available dataset with some ground truth to evaluate our model or to learn our model. So we had to generate some, and here is the process. So first, we choose a context to describe our anomalies. Then we take a graph. Then each node of the graph is given a color, and the color are seen as one-hot vectors. And among all the nodes, we can find the anomalies based on the context that we chose before. In our experiment, we used many different contexts to define our anomalies. So here they are. And the main difference between them is that in the A0, A1, and A2, we do not use the information of the node itself, so there is no bar over any letter. And in the context A3 to A6, we use the information of the node itself, and well, it may change things later. So how do we do it? We first choose a context. So in this case, it's the context A4, which is the node is yellow and it has at least one blue neighbor. And then we choose a graph. We give to each node a color, which is in fact one odd vector. And then we can find the different anomalies in the graph. So that the process to create data, but when we are dealing with finding the anomalies, we don't know the context, so we cannot use this information. In our experiment, we've used many different kind of graphs. So there are generated graphs and usual state-of-the-art graphs. And our method will be based on learning two classes classifiers. That means that we are learning at the same time two classifiers that can detect both anomalies and normal nodes. And we're gonna use attention mechanism that I'm gonna detail right now. So how does it work? This is the mapping function f that we discussed before. We input h, the matrix of features, and then the first step is to do a global affine transformation, lambda, which will be sigma, an activation function of h, the input, times w plus b, a bias. So we are gonna learn the weight matrix w and the bias b. The second step is to learn some local linear transformations. And by local, I mean for each attention head. So we will split the network into C parts. And lambda C will just be a local linear transformation. That is lambda times WC, where WC is learned during the process of learning. And the third step, which is, well, the main step of the process, is the attention mechanism, where we are gonna learn UC vector and the coefficient IJC, or just liquidity, which is another activation functions of something. This something is lambda I times lambda J, and this product is the product term by term of the two vectors, and there are a notion of similarity of the two feature vectors. And the dot product with UC will select only the best component to do classification later. Then we apply a softmax to have alpha AJC for each attention head. And in the end, we only have to aggregate the information. So the new representation HIC will be a linear combination of the lambda JC that we just saw before. And in the end, we will concatenate all attention head together and apply sigma prime, a new activation function. So in the case of the end of the network, it will be a softmax. And in the case of a layer in the middle of the network, it will be a ReLU activation. How did we train our model? So we split the data into three sets. The first set is the training set, which is made of 50% of our anomalies and as many normal nodes. We use also validation step to evaluate our model through training, which is made of 25% of the anomalies and as many normal nodes. But for the test set, we do not know, and we should not know, the number of anomalies. So In fact, we only take 25%, that is the remaining anomalies, and 25% of normal nodes also, that is the remaining normal nodes. And to evaluate our model, we will compare the results with 3 challenges, which are graph sage, the original GAT, so the graph attention network, and the GCN, the graph convolutional network. These 3 methods are also graph neural networks that have been previously published in the literature. And well, we've done our experiment, and we show that COBAGAD, our method, is able to very efficiently detect contextual anomalies with very high rate, and it most of the time outperforms all the other contenders. So to conclude quickly, we've seen today how to define contextual anomalies. We've seen how to generate a data set with ground truth with contextual anomalies. I presented COBAGAD, so a graph anomaly detectors that can detect contextual anomalies. And we've made experiment to confirm that our method is able to, well, detect anomalies very efficiently. And we plan to address interpretability, anomaly scoring, and experiment with real features. So thank you very much for your attention, and you can find the code here and reach us on our emails, of course. If you have any question, it will be my pleasure to answer you.